Hi everybody. So for those of you who are taking the PSAT, or if you just missed yesterday or today, I guess when I'm recording this, which is October 10th. Today what we did or are doing right now is solving a problem involving mu k, or the coefficient of kinetic friction. So that's the coefficient of kinetic friction. And I'm going to further define some of this coefficient stuff, but then I'm also going to solve a problem involving mu. Mu. So again, that's mu. Mu, the coefficient of kinetic friction. It's like a U with a bit of a flare at the end. So that's what mu looks like. All right, so let's go back to yesterday and see what it is that we're going to do. Just to remind you guys, some properties here is that mu is a unitless quantity. So it's the normal force divided by the normal force. It is newtons divided by newtons, so they cancel out, and it is a unitless quantity. Another thing is that the number, it tends to be a number between 0 and 1. So if it's 0, if mu is close to 0, that means that the smoother the surfaces are. If mu is close to 1, that means the rougher the surfaces are. And then also, this number, mu, depends on the material of the two surfaces experiencing the friction. So those are just some properties of mu. Some other things to consider is that we use the force of kinetic friction divided by the normal force for an object if it is moving. So if the object is moving, this is what we use. This is the relationship. However, sometimes we're going to see, especially when we start doing ramp problems, is that we use this coefficient of static friction as opposed to the coefficient of kinetic friction for when we're talking about objects that are just about to move. Just before the objects are about to move, we use the coefficient of static friction, where we use Fs max. So we use the maximum static friction divided by the normal force equals the coefficient of static friction. Both of these you can see either in your textbook or you can look them up online. So if you look up the coefficient of kinetic friction, that's this value. If you look up the coefficient of static friction, that's this value. So if you're talking about an object that's just about to move, you would use this relationship. And if you're talking about an object that is moving, you're using this relationship. Mostly you're going to use this relationship, kinetic friction. But every once in a while, you'll have to use static friction. And when we talk about an object just before it's about to move, that means that the acceleration of the object is 0 at that moment because it hasn't moved yet. All right, let's go into a problem. So here's the problem. You got somebody. Here's somebody. And they're moving a box. The box has a mass of 20 kilograms. They're moving it with a force, an applied force of 150 newtons. They're moving it at a constant velocity. And then also friction is present. So friction is present. So with all this information, I'm going to draw a free body diagram of the box. The box is my object. Oh, sorry, I should say we're trying to find out what mu k is. What is the coefficient of kinetic friction in this case? So I'm going to draw a free body diagram here. Let's see, I get the force of gravity. There'd be a gravitational force on the object. There'd be a normal force that would counteract that from the floor. Equal in magnitude, opposite in direction, because the box is not falling through the floor or floating up into the sky. Also, I'm using an applied force that's pointing to the right of 150 newtons. And then lastly, because they say friction is present, I'm going to show a friction force pointing to the left. And I'm going to make it equal in magnitude to the applied force, because the object is moving with constant velocity, and that means that the acceleration has to be 0. Once I do that, I then go, okay, now I'm going to do the second law. So I'm going to do the second law along y. The only two forces I have along y are the normal force and the gravitational force. The normal force is positive, so it's going to be Fn minus Fg. And it equals the mass times the acceleration along y. But again, because my object is not floating into the sky or falling into the earth, the acceleration is 0, so this term goes to 0. And if I add Fg to both sides, that will give me that the normal force equals the gravitational force. So that's one relationship I got right there. Next, I'm going to use the fact that I'm going to use the second law along x. So that's going to be the second law. So it's Fa pointing to the right, the force of kinetic friction pointing to the left. So that's going to be Fa minus the force of kinetic friction equals the mass times the acceleration along x. But if the object's moving at constant velocity, the acceleration along x is 0. So all this becomes 0. And that gives me, adding the kinetic friction to both sides, that the applied force is equal to the kinetic friction force. And that's another relationship I got right there. So lastly, I know that I need this. So I know I'm trying to find mu k. That's the goal here, is to find mu k. And I know that mu k, the definition of it is the kinetic friction force divided by the normal force. So if that's true, I need that kinetic friction force. And the kinetic friction force I could use from this relationship. I know that the applied force is equal to the kinetic friction force. So if that's the case, I know the applied force from this previous problem is 150 newtons. So if that's the case, I could say that the kinetic friction force is 150 newtons. So if that's true, there's that. Let's do it in this color, or this pattern. So next up I can go then, I need to find the normal force, so I can use this relationship over here. So I know the normal force is equal to the weight, and I have an equation for weight. Weight is mg. So I can replace the weight with mg, and that'll give me that the normal force is equal to mg, because I'm replacing Fg with mg. So I'm plugging that in there. And I'll get that the normal force is equal to mg. Well, m is 20 kilograms. And g is just the gravitational field, which is 10 newtons per kilogram. So, in other words, the normal force is 200 newtons. And again, I'm going to circle all that. So now, I got the normal force and I got the friction force. The friction force, I'm going to plug in there. And the normal force, I'm going to plug in there. That'll give me that mu k is the friction force, which I found out was 200 newtons. I'm sorry, I found out was 150 newtons. Divided by the normal force, which is 200 newtons. And I will get a coefficient of kinetic friction of about 0.75. Again, it's a unitless quantity, but there you go. That's my answer. And so there's an example of applying the second law and the ideas of friction with that coefficient of kinetic friction. So we'll do more problems tomorrow and in the future. Again, I apologize for my voice. I'm dying. So there you go. Any questions, let me know. All right. Bye-bye.